Hello, everybody. Happy Friday, and thank you so much for joining us. It looks like it's going to be a really good turnout for the number of people. We have almost 80 people logged in already, so this is a very popular topic. Hopefully, Ed will be able to cover all of your questions and things that you're interested in. So I'm just going to start off just with a little reminder about some of our upcoming events. So I'm going to go ahead and share my screen here. I don't know if you've seen in some of our newsletters and emails that have come out, but we've organized a 4-week webinar series that's starting in mid-January. It's going to run every Thursday for 4 weeks consecutively. They're going to be 90-minute webinars. And we actually have a leading speaker, Jerry DiMaggio, and he does a lot of presentations for ASCE, just all over the country on LRFD, that's load resistance factor design. And so the 4 webinars in this first session, the first one is going to cover load and resistance factor design fundamentals, and then the second part will add to that. The third one will be best practices for geotechnical site characterization. And then the last one will be design and construction of driven pile foundations. So just a quick reminder too, the CalGeo member price is $300 for this, which I believe is pretty good comparatively to some other ones he's done and how much they end up charging out at. And also, if you want to share this with any structural engineers or other clients that you work with, if you're a CalGeo member, I can give you a discount code where even for them being non-members, they can save $100 off the course. So let me know if you're interested in that. Again, that information is on our website. So I just wanted to do a little plug on that right now. And then we are going to go ahead and introduce Ed Hernandez here with Project X Corrosion Engineering. Project X is actually a newer affiliate member of CalGeo, so I know he's been following some of our events and things that we've done over the last couple of years, but they finally joined, and we want to let you know a little bit more about what they do and corrosion engineering in general. So Ed is from LA originally and graduated from Cal Poly Pomona as a mechanical engineer. Wow, he ended up in Finland getting his master's and learned some languages and is now back out here in Murrieta. So very close, lives close to his lab as well. And he has experience in the fields of corrosion control, positive material identification in the lab or field, soil analysis, water analysis, failure analysis, metallurgy, foundry engineering, and various forensic analysis methods. So I won't go into all the things, they're on our website, but without further ado, I'm going to go ahead and give Ed control here. So you can see his screen. Perfect.
Okay. Well, thank you, Kelly. Can you see my screen okay? Everything
Yes.
all right?
Yes, everything's great.
All right. I'll start now. And well, hello, everybody. Happy afternoon. And let's see if I can answer some questions and pull the veil of mystery away from corrosion for a little bit. I know a lot of people are always asking, what should we test for? What's important? And, what is the risk? And I believe in being practical about things. And yeah, you don't have to use cathodic protection always when it comes to corrosion protection. There are many ways of holding back corrosion. So that's where I think my background in materials and foundry and just this weird life experience of working in different types of forensics and civil engineering helped me think out of the box for some things. But let's see, there we go. So to begin, what's the real point, right? When we're building something, we don't want it to corrode, right? Definitely most people out there, when they wonder about corrosion, they just automatically believe that my geotech will know because you guys are the dirt people, right? But that's not the case, right? Geotech soil reports, they must be a corrosion expert. That's what people think. But as your reports state very often, and you make it very clear that the geotech company does not practice in the field of corrosion engineering. That's a great thing to let people know. It's usually at the very end of a corrosion section in your soil reports. So I have a feeling that a lot of civilians don't get to that last sentence sometimes. So I would recommend moving it forward. But I've pretty much had the experience that most people do not know that corrosion engineers exist, not until you mention it in your reports. It's pretty interesting. So now people are always asking, what do we have to do? And what's the law require? In reality, it's only sulfate and chloride are the required testing, in the building code. Sulfates are all about concrete. The chlorides are the ones that can really cause a lot of damage, very localized corrosion on metals, leading to leaks or other things. So those are two of the most covered and mentioned in the building code. But even then, it doesn't always make it a requirement to test for it. For example, the Caltrans corrosion guidelines, they'll say that if you have if your ohm centimeter resistivity of the soil is greater than 1100 ohm centimeters, you don't have to test for sulfates or chlorides or any of these chemistries. So that's kind of odd to me. And there's definitely room for improvement in the corrosion control guidelines for Caltrans. I tend to believe that the Caltrans guidelines are more focused on highways and bridges or those type of things, and not necessarily residential building or business parks or sky rises, where you will have many more types of alloys of metals and electrical grounding grids and so forth. So a lot more variety in metals that can be in a job site. Every metal has its weakness. So the Caltrans corrosion guidelines tend to focus more on recommendations for steel. All right, so let's see. And the funny thing about the corrosion guidelines offered by Caltrans is that there doesn't really seem to be a gray area. It's either corrosive or not corrosive, if you are at any of these thresholds. And there really should be a gray area. So here's an example. It is possible to have high amounts of chlorides in a soil, even when you have a soil resistivity over 1100, as you can see in this chart. So as you can see in this chart, this is where that 1100 line would be for Caltrans. And you can have chlorides up to the 800s parts per million, 600s, very easily, way up there, over 400 parts per million sometimes, So the point of this is basically you don't know until you test. So the building authorities, like the cities, the counties, and so forth, water districts, often they've suffered some failures that led to them not wanting to suffer those type of surprises ever again. So they've been requesting more and more letters from corrosion engineers for various projects. So to avoid surprises, it's always a good idea to get at least a couple of soil samples from a site and test it for full series. And my full series for a corrosion engineer is minimum resistivity, pH, chloride, sulfate, nitrate, ammonias, sulfides, and redox. It's 8 different tests, whereas geotechs and the Caltrans guidelines typically recommend 4 tests. So that's one difference. So something that I get asked a lot, are all corrosion engineers the same? And the flat answer is no. You know, we all specialize in different things. Anyone can be a corrosion engineer. You can be a mechanical engineer, a materials engineer, an electrical. There is no corrosion major in most universities except one in the University of Akron. But there is no longer a corrosion PE like there used to be. That ended in the year 2000, I believe. So there's many corrosion engineers, all they do is cathodic protection. That's all they do, and that's all they know. Some work at refineries, so they're more familiar with internal corrosion of plumbing, or just refinery pipe work and things like that. So other corrosion engineers are coating experts. All they do is coat tanks and bridges, maybe, and they examine the coatings for defects or things like that. So there's a lot of different types of corrosion engineers. Corrosion engineers that are mainly into forensics, failure analysis, and chemistry, soil chemistry analysis to predict corrosion rates and to provide corrosion control recommendations based on those results. There's not too many of us, that's for sure. So, one thing to always keep in mind is what could go wrong, right? So, this is real strange, by the way, not being able to hear the crowd or see any faces. I am getting no feedback. I hope everyone is still online and hopefully not falling asleep. But anyways, what could go wrong? This is a pipe leak in Los Angeles. That's a stainless steel bolt that was eaten from the inside out by corrosive bacteria. It's a 304 stainless steel, by the way. Down to the bottom left is a ductile iron pipe corroding in a very corrosive soil in Compton area, where ductile iron is very interesting because when it corrodes, usually the iron is leached out of it, but it leaves behind the graphite matrix, and it's still black, so it's very difficult to tell if it's corroded or if it's lost its integrity. So if you take a magnet and run over the surface of that pipe, you will feel the magnetism disappear. When you get to the areas where the iron has been leached out, and basically that's what happens. The iron leaches out to the point where the pressure, internal pressure of the inside the pipe, breaks through that mortar lining inside the pipe and pops the cork of the graphite. Here's another in the middle, a picture of a copper pipe that suffered high attack from ammonia and nitrates. And this is a pre-stressed pipe. These are the big pipes usually used in the aqueducts to carry lots of water between San Diego and Los Angeles and all of the dams. So when they explode, they make a big boom. Now, something that most people are not aware of is that there is corrosive bacteria. Typically, there's many forms, many types, but in general, there's 5 corrosive bacteria that are most commonly tested for and that contribute to a lot of corrosion situations. Some are anaerobic, meaning they need oxygen. They do not like oxygen, and some are aerobic, they need oxygen. And oftentimes, these 2 bacteria will work together. So that's what's showing here, a cross-section of a tubercle. See, this is a protective biofilm dome that they form, and the anaerobic bacteria will start to settle inside under the dome, and it's their byproducts that are very corrosive and lead to the rapid degradation and corrosion pitting, typically, of the metallic substrate down there. So these things, they're like bacteria. It's like when you don't take care of your swimming pool, it just starts to spread, algae everywhere. And here's an example of tubercles inside of ductile iron pipes. They cause some severe pitting of that pipe all the way through the pipe. And this here is a picture of a 304 stainless steel bolt that was attacked by this corrosive SRB, sulfate reducing bacteria. Now, actually, that's the nut. The nut is what's suffering all of the corrosion. That's made out of 304 stainless steel. Everything else, the band and the bolt here, they were 316 stainless steel. and didn't suffer any corrosion. So let me go over a little case study. I think that's where I was going with this, but this is selective iron leaching. I ran a magnet over the surfaces of this pipe, and I drew this dashed line wherever the magnetism seemed to disappear. The images that came out after from these outlines look pretty nasty, I'm sorry, but basically you get an idea of where there is iron and where there is no more iron. Basically, this pipe was turning into Swiss cheese, and that's why it was popping leaks. Here's a cross section of one of those areas. So you can see the iron was completely, it's removed, it's leached out, and it just looks like you have a lump of clay back there. So when that area grows large enough, the pressure inside the pipe will be too much and it will break through it basically and pop it out. And that's what's happening in those ductile iron pipes. Excuse me. So something else that most people aren't aware of is that galvanized steel is a great thing above ground, but underground it's not very, it doesn't always last too long, depending on the soil types and so forth. But the other thing to keep in mind is that when you bend galvanized steel, you can be causing damage. This is a dye penetrant test of a formed galvanized steel pile, basically. And the way the dye penetrant works is you clean off the surfaces and then you spread a dye that seeps into all of the micro fissures and micro cracks inside of the surfaces. And then you wipe all of that away, but the dye remains inside of the crack or any micro cracks. And then after that, a developer sprayed on, and it absorbs the dye seeps out of the crack onto the developer, revealing where those micro cracks are. So that's why the edges, these curved, bent edges of the galvanized steel, are reddish because this area is full of micro cracks, and the flat areas here have no micro cracks. It's basically all right there, and that's why it turns red. Okay? And there's a metallograph of a cross section of that bend, so you can see that when you bend galvanized steel, it will crack that protective zinc coating, and your corrosion will occur even faster at those areas, and that's why. So a lot of people have the opinion that galvanized steel will survive forever and anywhere, and it's not necessarily true. It's great for atmospheric corrosion resistance and situations, but even then you have to think about, is there a lot of moisture, tropical, is the design going to pool water, or anything like that? Or now with all these solar structures, I'm noticing that there's a lot of cars parked under these solar parking lots, and the exhaust from the cars are causing the galvanized steel to corrode faster on those supports on the roof. It's pretty interesting. So again, like I've mentioned before, galvanizing, it's great for the atmospheric corrosion. And in soils, if it's very low soluble salts, very low chlorides, very low sulfates, very, very high resistivity, then you can just bury galvanized steel into something like that. Yeah. So, but you don't know what the situation of the soil is until you test the chemistry of that soil. So there you go. Now, this is very important because a lot of people try to determine a site's corrosivity by doing a Wenner 4-pin test at the site. Now, how do I summarize this? I'm trying to remember. In the Caltrans method for soil resistivity, the standard for measuring minimum electrical resistivity, basically it points out that when a 4-pin is for eyeballing a hot spot for soil sampling, but it's not for estimating corrosion rate. Because you have to think, when you go out there, the soil may be very dry. Remember, in our laboratory, we test soil samples in a soil box as received and then as minimum resistivity. Very often, the as received is very dry already, and it's just extremely high in soil resistivity, ohm centimeter. But once you add a little bit of water to it, get it up to 20% moisture content or so forth, then you it falls dramatically. It'll fall dramatically at 10% moisture content often. So there's a big difference between those two. And if you're doing 1 or 4-pin testing in the summer as opposed to maybe in the winter, you're going to get completely different results because moisture content of the soil makes a huge difference on the results. So you should not use that field 1 or 4-pin data for categorizing the corrosivity of a site. Okay. Basically, 1 or 4-pin is supposed to be used for designing electrical ground beds and anode beds. It's about trying to figure out actually your worst case scenario, the address, like what kind of resistance the soil gives when it's dry, or so forth. Because that's very important for the electrical engineers to know, because if in the summer the soil is very, very dry, then that's going to be a very huge electrical resistance, and they need to know that so that they can design that electrical grounding system appropriately. See, so that's the main purpose of 1 or 4-pin. Now, the soil box is basically a 1 or 4-pin test, but in a box. And the reason where it's important to find the minimum resistivity by adding the moisture is because when you have pipelines or piles underground, there is condensation underground. So basically, there will be moisture up against the metals underground, and the soil in contact with that metal will now be at a saturated situation. So basically, a minimum soil resistivity. So that's why it's important to get the minimum soil resistivity number and categorize your site's corrosivity using that, as well as the water-soluble salts. The chemistry matters too. So let's see. And just something else to point out that I've seen in some reports that should be a red flag. There's this EPA 120.1 test method for testing resistivity, and it's not really a resistivity of soil. So what's happening is that in the laboratory, you'll create your extract by taking 100 grams of soil and 300 milliliters of distilled water and mixing that in a flask. And then many environmental laboratories, you could say, what they do is they take the liquid extract, filter it, and then they start running it through their machines, and they test the conductivity of that liquid. Okay, and the inverse of conductivity is resistivity. So basically what they do is just take the inverse of that conductivity read and determine resistivity, and that's what they report. But with all the filtering and so forth that they've done, they've removed many of the contributing factors of that soil. So that's not a good way to measure soil resistivity. So just to show you, we did an experiment in our lab where we were comparing our soil box methods and that EPA 120 method. And the results were all over the place. I mean, there were differences of 3,000 ohm centimeter and sometimes much greater. I mean, 10,000 ohm centimeter. There's a lot of differences there. So if you're going to be getting results from other laboratories about your soil resistivity, make sure they actually use the soil box method, not this EPA 120 method. So soil resistivity, the one thing to keep in mind is that it can change from acre to acre. Honestly, it can change even from just every 10 feet. It just depends on the variety of a site. If it's a farm, it's usually more uniform because it's been tilled and mixed and so forth. But there seems to be a site, usually on a farm, where somebody dumped something and who knows what the hell was going on, like in this one spot. And that's usually because that was where just all the chemical bags or something were placed or dumped, and it all seeped into the ground at that one area. So it's good to keep that in mind. That it just we always recommend to test a soil sample every acre in a grid pattern, so that if you do end up with a hot spot, you can just knock out that grid as being the hot spot, and you are confident that the rest of your site is not super corrosive. If you just collect 2 random samples from a 20-acre site, you're going to have to go with the worst results, because you can't take any chances for liability. So when it comes to soil resistivity, chemistry, there are 8 forms of corrosion, but but in this slide, what I'm trying to point out is that even if there's high resistivity, you can have those high chlorides or sulfates. There are some forms of corrosion that can still occur, such as the pitting, the crevice corrosion, the stress corrosion cracking, and fatigue corrosion. Okay, so corrosion, you have to think of it in a way that there's general corrosion that occurs over a large surface area, and then there's localized corrosion, that's pitting in small localized areas. So when it comes to resistivity, it gives you a lot of information about the probability of general corrosion. But the salts, the chlorides, the high chlorides, high sulfates, sulfides, nitrates, those can tell you the probability for pitting and that type of localized corrosion. So it's important to know both. This is a case study of a fire riser. This happens very often. I don't know why it's not in the building code to simply put the isolation joint in there. But anyways, what happens is often you have this short 8-foot piece ductile iron pipe underground that connects to PVC water main line, and then at 90 degrees up into a building to a flange at the floor, and then enters the rest of the building. And once it's in the building, there's a lot of meters connected to it, and a lot of electricians like to ground their equipment onto these pipes and so forth. And somehow it ends up also shorted to copper water piping in the building. And now, in the end, what you have is this short ductile iron piece of pipe that is now electrically continuous to a large surface area of copper in the ground. And so basically what you end up setting up is a giant lemon clock. I don't know how many people have played with lemon clocks or potato clocks, where you take a copper nail and a zinc nail and you punch them into the lemon or the potato, and then you connect a little LED light or a clock, a small LED clock, connect the wires to the 2 nails, and it will run, because that's how you make a battery. And batteries are basically corrosion cells. So it's one very noble metal consuming a less noble metal. That's called as part of the galvanic series. So I won't go too deep into that, but that's basically what would be happening in this type of situation. And all one would have to do to stop this is insert a gasket called a electrical isolation joint, where there's a gasket at the flanges and sleeves around the bolts, and this prevents electricity from traveling from underground to above ground. And basically it cuts the lemon clock like a switch, and that stops corrosion. So that is a form of corrosion control. So this is probably, when it comes to the majority of corrosion problems out there, it is because of dissimilar metal coupling that are not compatible, or just forgetting that there should be a dielectric union between them. A dielectric union is a piece of plastic or something that doesn't allow electricity to flow through. Right? But that is the largest portion of all the failures out there. This is an example of copper connected to a steel iron pipe. See, so the copper is much more noble than the iron. See? So basically, in the end, our clients just don't want surprises. The bottom line of the main thing to understand about corrosion is that corrosion is a big picture situation. It's not just about the bolt. It's not just about the pipe. It's about what it's connected to, what is it entrenched in, what's it living in, and what's flowing through it. Those type of things. There's a lot of factors involved. So to cover all of those factors, you basically just have to do your homework. So that's why we recommend, the surprises that we've seen from most of our clients is that at the last minute, the city, the county says they want a corrosion engineer letter, a corrosion study of the site, and the client is already practically putting the pipes into the ground. I think some people have experienced this in Chino, in Corona, Summerlee, all those type of things. And that's the worst time to find out that your soils are super corrosive, right? So that has happened. So there's that. Other surprises are the rebar corroding in the concrete before, much faster than anticipated, the post-tensioning anchors corroding, fence posts corroding, tie downs corroding within 5 to 10 years. All of this happens, so these are the surprises that you can avoid by just doing the homework of a corrosion study first. And that's why we recommend testing those 8 different factors. So this is the little cheat sheet I made to kind of help you understand which material is affected most by which ion, basically. So there's the low resistivities, the pH, the sulfates, the chlorides, the nitrates, the ammonias. These are all affect different things. As you can see, copper and brasses are greatly affected by the nitrate and the ammonia, whereas steel, not so much, right? But this thing that very few people are aware of are the corrosive bacteria. And to test for the probability of corrosive bacteria in the soil, you test for redox and for sulfide. So basically, if you get pretty high levels of sulfide and very low redox levels around, less than 20, and especially if they're negative, then there's a real good chance that you have corrosive bacteria. These kind of low redox numbers pop up a lot up north in the San Francisco area, but not too much down here in Southern California. Let's see. And then the other big question.
I wanted to jump in. Sorry, do you want me to launch any of our little poll questions?
Yeah, sure. Actually, after this one, I'll just point out this one about what to test. The big question I get is what to test. And my advice is basically, it all depends on how expensive is it if it fails. If it's a sidewalk, that's easy to fix. No big deal. Just test for your sulfate and maybe in your chlorides, and you should be fine. But the more expensive it gets to fix, the more I recommend you test. All right, go for that polling question.
Okay, which one? The ones about the metals with each other, or which causes more damage?
Take your pick.
Oh, okay. Let's start with this one. Okay, guys, so you should see a little blue quick poll window pop up. Try to select that, or maybe minimize your screen if you don't see it. And then the question is, are all metals compatible with each other? And you can choose yes or no. Pretty simple. I'll give you a few more seconds. Everyone's just voting in right now. We're at almost 70%. And we do have almost 120 people online right now, so this is good. Okay, everybody's saying 100% no.
Good, they paid attention. Well, maybe.
Do you want me to do the next one, or we'll save that for the end? Oh,
Do the next
okay. So the next one I
one.
have is what causes more corrosion damage? Is it sulfate, chloride, or maybe some of you are not sure? It's okay if you're a newbie. That's why you're here. And we're at almost 50% voting. I'll let it get to around 75. And it's a little bit mixed right now. So I'm going to share these results. 26% say sulfate, 60% chloride, 15 don't know.
Got it. Chlorides cause the most corrosion damage. Sulfates are mainly all about concrete integrity for the most part. What you really want, if you really want to know if your site is extremely corrosive to pipelines and to just say your blow offs, your air vacs, your fire hydrants, the water laterals that are going to be going into the residential homes or into the building, your chlorides and extremely low and low soil resistivities are the things to be looking out for. Chlorides will show you if you're going to have that probability of very localized corrosion, and your low soil resistivities will tell you if you're going to have like large general corrosion areas where a copper electrical grounding grid, in the same area will affect will affect a ductile iron pipe a few 100 feet away. So that is facilitated when the area has a very low soil resistivity. So those are just the general concepts. Let's see. Did we have more of those polling questions? I don't remember what we came up with.
No, we just had the two.
Okay, no, that's good. Yeah, guys, I'm trying to keep this interesting somehow. But yeah, it's. But if anyone has any questions, you can email me, text me on WhatsApp, or my contact information is at the end of this presentation. So yeah, I'd love to answer questions. And Kelly's going to help me put together a frequently asked questions for this corrosion. Let's see. So one chart that has been useful for some of my clients is this, basically, that if you have high groundwater, low resistivity, soil resistivity, expansive soils, and high salt contents in your site, you are in a lot of trouble, basically. Basically, high groundwater, if it's very high, some places have it, just 5 feet under finished grade. This will act like a splash zone, just like splash zones at the beach, underground. And if they're hitting your pipes or your infrastructure underground, they will corrode faster than normal because of that splash zone. The low soil resistivity, we've already talked about, just accelerating general corrosion. Expansive soils, the thing about expansive soils is that they reintroduce oxygen deep into the soil. So when there's more oxygen, there is more higher corrosion rate. So out here in by the Fulton Sea, there's fissures in the ground that we can drop a 5-foot stake into and it completely goes in there. So you can expect very high corrosion rates, even down to 5 feet, because of this. So that's something very important to keep in mind, especially for solar farms and piles. And then the high salt contents, high chlorides, high sulfates, high nitrates, all of those things. The more of that, the more corrosive the site is. One easy rule of thumb is like farms, wherever anything grows easily, if there's a ton of vegetation somewhere, then it's a very good sign that that's a very corrosive site, because obviously there's a lot of nutrients in the ground, and there's a good plants grow best in low soil resistivities. So, because they have to have that ion exchange too. So a lot of vegetation, a lot of, you're like, wow, this is a tropical jungle here. Yeah, that's a good sign that site is very, very corrosive. Now, this is interesting. I've been experiencing this with a few developers lately, that they want to do a preliminary corrosion study for their due diligence, and then they'll do a more detailed corrosion study afterwards, after the rough grading. So in the preliminary study, because what we've seen sometimes is they'll have undisturbed land and they don't know how corrosive it is. So we recommend collecting every 5 acres, something more spread out than normal, just to get an idea of how corrosive that site is, so that when they begin grading, they don't push all the bad dirt into the rest of the site. So that keeps the site from becoming more corrosive than it actually was. Yeah. So like I said, resistivity alone will not spot the hot spot. So just going out there and doing the 1 and 4 pin testing is not the way to figure it out, especially in the summer. You're just lying to yourself. So that's something to keep in mind. And for the final corrosion studies, where usually the pads are prepared, that's when we recommend testing in every acre in a grid pattern, so that if any hotspots do occur, we can minimize the conservative recommendations, corrosion control recommendations, to a very localized area. Sometimes by collecting just a few samples around those hotspots, we can isolate them even further to just one lot, which can save a developer, I've been told, up to $3,000 or $5,000 in concrete additives and so forth per slab. So that can add up quite a bit, and when you consider that every soil test is only $150, that's definitely a good investment to perform a good corrosion study. So the other piece of advice, by the way, is I recommend you not collect soil samples close to concrete curbs or walls, because I believe the winds tend to collect a lot of things up against walls, and a lot of times we see hotspots be at these locations, near walls, near concrete curbs, and it may just be remnants of the concrete mix, powder, something, just got into the dirt and kicked up the soil's salt content, and maybe lowered its resistivities. But mainly it's about salts, the water-soluble salts. So try to stay away from those type of areas, just to not get these false hot spots, basically. Soil sample. Oh, these are just the general recommendations of where to collect soil samples. For pipelines, we recommend you collect them every 1,000 feet from the depth of the pipe. It's very important that when you're trying to figure out if something is corrosive for some sort of infrastructure, you want to collect the soil sample from the depth of the infrastructure that it's going to be in. If you're worried that you have skin cancer on your foot and the doctor takes a sample from your ear, it doesn't sound like a smart idea. So, like a good approach. So you want to collect soil samples from the depth at which the infrastructure is going to be installed. And preferably, you don't want to mix soils. If you drilled from finished grade down to 5 feet, you don't want to send a mix of all of that, 0 to 5 feet, to the laboratory for testing, because it's going to be a diluted sample. You may actually have a very corrosive strata deep down, but you won't be aware of it because you mixed the soil with the maybe very non-corrosive soil above ground, or not above ground, but higher closer to finished grade, and it dilutes. So you may have a surprise pipe leak, or utility problems. So that's something to keep in mind. Then typically, so for soil samples, for slabs, 1 foot depths are good enough. For utilities, they're typically around 3 feet deep. And then elevator pits and underground parking, you want to get them a couple samples from every 5 or 10 feet, depending how deep this whole thing goes. And like I said, collect from every acre or every 5 lots. Back when I was at Schiff, I think most of our clients were collecting every single lot and testing every single lot. So that would be great too. So when I guess this is the moral of the story here, we're getting there. What is the practical approach to corrosion control, right? So now that you know, corrosion's a very complicated thing, you can say, but at the same time simple. Um, is cathodic protection the only option, CP? And no, it's not. Definitely not. It's the last resort. Um, so the other options are coatings, material selection, choose the right material for the job. Then additives or changing the resistivity of the soil or the environment, or then maybe cathodic protection. But remember, a lot of things like steel, they do not corrode in high pH environments. And cement and concrete is a high pH coating. So simply coating things with concrete can provide corrosion protection for steels most of the time. So which one is the least expensive option? It just depends on the estimator. I've seen estimators for some reason choose one option versus others, like different estimators, I mean. And they just have contacts that can get them for better prices. I have no idea how it works. So that's why usually I try to provide as many corrosion control options as possible, because who knows what's least expensive that day. So yeah, and the conservative recommendations, should they only be for the hotspots? Of course. Now I don't believe in applying conservative corrosion control recommendations to an entire site if we have collected enough data to confidently knock out a hotspot. And I believe it's a good approach for saving a lot of money. So, like I said, one of the biggest surprises that people get on many sites is not knowing that there are high chlorides in the site. And that's because everyone was simply testing for sulfate. Sulfates because that's what the building code requires. But like I said, sulfates are just for concrete integrity. So at a minimum, I recommend you test for sulfate and chloride. So let's see if just something to cover. If for sewers, which are typically very deep and usually very, very low oxygen levels down there, if the metallic fittings are wax taped, wrapped, then testing for chlorides and sulfates and this kind of chemistry at those levels can be skipped, because wax tape is a fantastic coating for separating soil from the metallic surfaces. So that, and they will stop the corrosion very well. So that's it. If anybody has any questions, feel free to send it over. Like I said, this webinar method is very strange because it's so quiet. I hope everyone has had a good, hope they learned something from this. So
yeah, it's a great presentation. We have quite a few questions come in. So early on, we got a question asking if you could discuss and clarify the difference in resistivity measurements. For example, minimum, saturated, and what should be considered or applied in design.
I see. Yeah. So there, as received, a as received electrical resistivity measurement would be, say, you take the soil straight out of the bag into the soil box and read it as is without adding any moisture, any distilled water to it for the testing. That will come out very high, usually like 10,000 ohm centimeter, sometimes 300,000 ohm centimeter, depending on what the soil is made of. The more silica, sandy the soil is, the higher the resistivity it will be. It's, silica is like glass, not a good electrical conductor. But if the soil has a lot of clay, organic materials, a lot of these finer particles and clay especially is a very good conductor of electricity, and that's when the electrical resistivity is lower. So once you start adding distilled water to these, the minimum resistivity versus the saturated, they are basically the same, but sometimes since some soils are a bit expansive, as you start adding the water to the soil, it will the electrical resistivity will drop, and then it will start to rise again because I believe voids are starting to form inside of the soil as it's starting to swell, and those pockets of distilled water, which are not very conductive, start to contribute to raising the electrical resistivity. So that's what this minimum electrical resistivity is. It's all about what's the very bottom. Saturated, it's when you do a saturated soil resistivity, the approach is to basically just fill that box with as much pooled water as you can, and take the reading. And that might be just a tad higher than what a minimum resistivity would be, but very, very close usually. Hope that answered the question.
Yeah, great. So the next one, sort of two parts to this. What kind of site conditions are typical of bacteria corrosion, and what testing methods are best to detect corrosive bacteria? So the site conditions and how do you test for it?
Usually there's a lot of clay, peat, a grayish type of clay or black clay. That's a very common look for these things, and it'll have a bit of a sulfur smell sometimes, like a rotten egg. If you have a really bad site, you'll have a rotten egg smell to things. If you sometimes if you find a piece of metal and you have some, if you're carrying around some hydrochloric acid, what you would do is you take a drop of the hydrochloric acid and drop it on the rust of the metal that is maybe in this bacterial corrosion problem. And if what you smell after putting that drop of hydrochloric acid onto the metal, the rust, if you smell sulfur instead of chloride, that's a very good indication that you have sulfate reducing bacteria in that corrosion product. And the site probably might be experiencing that. So that's why. So the important test for sulfate for detecting the probability of corrosive bacteria is the redox and the sulfite. Typically, it's in literature it says that if you have very high redox, that means you have a lot of oxygen, and the likelihood for this corrosive bacteria is less likely. But when you have very low redox or negative redox levels, that's when your anaerobic conditions are existing, and bacteria love that. That's the answer.
Okay, perfect. The next question is that they see a wide range of estimates for corrosion rates of galvanized piles, excuse me, supporting solar PV structures. Are there any guidelines they can follow?
I'm not sure how to answer that. It's tough because some people try to take the approach of, okay, the corrosion rate of a pile underground at a site is going to occur, that the steel, some people calculate things in a way that the steel will not start to corrode until all of the zinc coating is consumed on the outside of the underground portion of that pile. And that's not how nature works. Usually it just starts at a spot, and once a area of, you could say maybe 3 or 4 inches of galvanized steel has been removed from an area, very often, just because moisture in the soil is usually not homogeneous. It's kind of like, almost looks like a web of varying moisture trails, and the majority of the corrosion is going to occur where it's actually up against that wet area. Okay, and like I said, it just, condensation tends to occur at some areas right up against the metal. So, yeah, it's a tough one, but basically we usually use a mixture of AASHTO and Caltrans corrosion rates estimations for corrugated steels and some other corrosion rate estimations based on these 40-year study from the National Bureau of Science and the Romanoff books to come up with a mixture of potential estimated corrosion rates for the zinc coating and for the steel substrate. Other ways of estimating the corrosion rates is to get the soil sample itself and to use a LPR method, which is a linear polarization rate. You put this meter into the soil and leave it in there for a few days to actually measure the corrosion rates that are occurring on those metals in that soil. And that's also a great way to come up with a quick estimation and actual corrosion rate. But it is funny how, especially in expansive soils, the corrosion rate it's not constant. It jumps up and then down, and then all of a sudden it just pops up out of nowhere for God knows what reason, as the soil is wetted and dries out and wetted and so forth. Did that answer that question?
Yeah, that was great. Okay, we have a couple more, and just to respond to everybody, yes, we will have a recording of this presentation. We'll put it on our online learning library, so you can watch back. If you have to leave right now, we'll continue to record all the Q&A. And if there's any questions that we don't get to, like I said, I'm going to create a report of all the questions and send it to Ed so he can respond to you directly. So anyways, the next question talks about ACI calls for determination of sulfate sulfate category by ASTM C1580. Can you comment on the comparison of this test method versus the Caltrans method for sulfate determination?
I'm sorry, I missed all those numbers. What was it again?
Yeah, it's basically comparing ASTM C1580. So that's how ASTM says you should determine the sulfate category versus the Caltrans method.
Oh, well, it depends because there's in the Caltrans method. Well, now it's with an ion chromatography. It depends on what system you're using and what year of the method you're using, because there's ion chromatography methods, there's spectroscopy methods, and there's a titration methods. So typically, we've tested the sulfate test methods. Was this about sulfides or sulfates again? I can't remember what you said.
It was sulfate, yeah.
Sulfate. So we've tried testing for sulfates in various different methods, and sulfate's actually one of the most consistent ones that comes out no matter which method you test it by. It actually comes out very similar across the board from all of the test methods in our experience.
Okay, that's easy. So doesn't really matter too much. Okay, so the next one is, what is the corrosion risk in rock and how would you evaluate it?
It depends. Typically, in rock, it's usually very little. Like in Kentucky, where everything's installed in just, you just dig 2 feet and you're in a rock, into bedrock and so forth. So your corrosion risk is much, much lower. There's no very low corrosivity actually in those areas. So the only challenge is that if you say you're laying gas lines, pipelines, and you're required to put cathodic protection onto those type of pipelines, cathodic protection, electrical currents don't travel through rock very well, if at all. So that's the challenge. Now they have to figure out a different way of cathodically protecting that pipeline. But in general, no, very low corrosivity environment if you install things in rock.
Okay. And then this next one is asking about the amount of soil sample necessary for a full suite of corrosion tests. What would you recommend?
Yeah, you only need 300 grams of soil sample. So a soda can, basically, it fits in a sandwich bag. That's all you need. It's easy to mail. So just a plug. But yeah, that's all you need to be able to do the soil box test and create the extract for the Caltrans extracts and to test for the various water soluble salts.
Great. So this one we might leave as our last question. It's a little bit longer, but I think it's applicable. So as consultants, we're often asked to provide a qualitative opinion as to the corrosivity of site soil. As you noted, there are many sources of corrosion, yet there appears to be little published data or charts indicating the corrosiveness of the soils based on test results. Is there a reference that presents such information, including sulfate, chlorides, pH, resistivity, nitrate, ammonia, redox, and sulfide combined for different material types?
Sort of. Remember, most of those charts that are out there are material specific, and you have to remember that. When someone asks you, is my site corrosive? You should ask, corrosive to what? Corrosive to steel? Corrosive to copper? Corrosive to brass? Aluminum? Which one? Because every metal has its weakness. So there is, something like a AWW C105, which has a nice chart for determining if a site is a bit corrosive to ductile iron, cast irons. But that's very specific for iron. And then usually the Army Corps of Engineers, I think, or even NASA. NASA has some great stuff. The Navy has a lot of stuff on corrosivity and trying to simplify these things. But again, it's all about, you have to keep in mind what material you are worried about. If you do a lot of residential, you really want to worry about coppers, brasses, because when people start springing leaks on their water lines to the houses after 7 years, it's just hell. Those construction defect lawsuits just start piling up and so forth. So you just have to remember things that used to be a dairy farm or something that had a lot of fertilizer on it before. Since copper is so threatened by ammonia and nitrates, you just should keep that in mind, for those type of sites. But if you're just going to be doing steel, basically, then you can just go with Caltrans guidelines. Did I cover that? I can't remember.
Yeah, perfect. So we will touch on just the last few short questions individually with everybody if we didn't get to you, because it's a little after 1 o'clock, so we'll let you guys all get back to your Friday afternoon. Thank you so much for signing in and joining us today. And Ed, thank you so much. That hour just flew by. Super interesting. And have a good weekend.
Well, thank you all.
Okay, bye.
Bye.